be considered lawful by the courts if challenged. With regard to the issues I have reviewed and discussed briefly, let me recommend some required courses of action. We need a US policy which enables the private sector to enhance its competitiveness. Corporations should not be prevented from taking necessary actions when the realities of domestic or international competitions require it. Of course, such actions must be lawful and lend themselves to the promise of increased productivity and profitability in areas of long-term economic significance. One such area is cooperative R&D ventures. Cooperation in the development of technology may not only be beneficial, but necessary. We need a change in the tenor of current laws, from laws that sometimes permit technological cooperation to laws and legislation that encourages it. The clarification or modifications required are minor relative to the legal framework within which the creation and exploitation of technology must take place. However, the changes should not interfere with the free market mechanism, nor should they require any intervention in the market by government agencies. It should be clear from my previous remarks that I am advocating against a comprehensive national industrial policy which, as history has proved, is most certainly doomed to failure. Why? Because resource deployment is likely to be ineffective and therefore harm rather than enhance United States competitiveness in world markets. But what role should government then play? The key is to substitute intervention with participation and collaboration. In addition to its own directed R&D activities, government agencies can, compatible with national interests, grant subsidies to privately managed research and development programs. This will not violate the benefits coming from a free market mechanism as long as government does not assume ownership responsibilities and abstains from participating in the management of resources, including capital. The main purpose for participation should be to accelerate results, broaden the scope, and provide added incentives for private investments by lowering hurdle rates. I believe that all of us can see the separate pieces of the problem. The challenge is pulling them together, sustaining new action, and streamlining the solution. There is no reason for broad pessimism. There's a lot that is working exceedingly well in the United States, including capital, availability and formation, entrepreneurship, initiative, scientific and engineering capability, management, marketing capability, etc. On top of this, government is taking constructive steps in support of high tech. The budget proposals to Congress for 1984 include large increases endorsing areas relevant to research and development. There are many bills on the way in Congress that deal with science, technology, innovation, and education. Today's tax policies are more favorable to research and development, although I urge legislation making tax credit provisions permanent versus the temporary measures under the Economic Recovery Act of 1981. But it is too early to stop. More is needed. The recommendations as released earlier this month from the President's Commission on Industrial Competitiveness are encouraging. The shaping of U.S. government policy substantiating requirements for industrial competitiveness both domestically and internationally, and in private sector response would strengthen the U.S. in the high-tech race. The Japanese and the Europeans do not think the US has lost the high tech race, and neither should we. By sorting out the priorities, by producing incentives to invest, by getting the right things done and done urgently, and by eliminating institutional deadlocks and bureaucracy, US business will be positioned in the forefront to exploit the great opportunities we see for future growth. Thank you.
Thank you, Bill. We have time for questions. You can either send me questions on these cards, but in order to save time, I would welcome anyone to stand in their place, and as Steve reminded us this morning, shout loudly and address your questions to our speaker. And I may not be able to see you with these lights here, so speak up. There's one.
Do you see any advantage at all to an American meeting?
The question is, do you see any advantage to an American MITI? My answer is definitely no. I don't think the system is transferable to the US environment, and I don't think it's the right way to undertake the activities needed and generate the results which are required.
I wonder, in another field unrelated to computers, but the recent decision of the FTC blocked merging of Smidt with Baker Steel Corporation, in part intended to allege process optimization, does not order poorly for the kind of concern you have for improved attitudes on antitrust policy and the ability to achieve some of the goals recommended in the law.
The question relates to a recent decision by the Federal Trade Commission as to a merger within the steel industry and whether we see any concerns of those kind of decisions relative to high-tech, for instance, joint R&D ventures. I don't think there's any direct correlation between a merger of existing corporations and the considerations that anybody will embark upon, whether that is advantageous or not, and then the considerations surrounding an establishment and operations of R&D joint ventures. They are two very different issues. I do think that the Antitrust Division's possible application of formulas to check whether things are reasonable in terms of whether they should happen or not when it comes to mergers certainly should not be equally applicable to R&D joint ventures.
Clarify that? My question perhaps wasn't clear, and I don't want to sound like a spokesperson for the steel industry, but the allegation was that the merger in both instances would have permitted a modernization and productivity to allow them to become competitive with Japanese-produced steel. So I think the analogy is actually more apt than perhaps my first question might have indicated.
Well, I think my remarks earlier clearly indicated if you lawfully can pursue productivity increases, it should happen. Otherwise, I think from a competitive point of view, you're walking down a dead-end street.
Yes.
The joint R&D venture that you're involved in brings in the larger firms. There have been a number of studies that indicate that a great source of innovation, in fact even a more significant source of innovation, is the small business. What would you see as being an appropriate government role to influence the investment climate for small businesses? New starts, that sort of thing.
The observation is, and the question implied is, since the participants in MCC as a joint R&D venture primarily are large corporations, and the observation was also made that since a lot of innovation take place in much smaller entities, what should then happen in order to foster that type of environment? First of all, let me mention that the fact that there are large corporations as shareholders in MCC is certainly not an exclusion of the capability to incorporate much smaller entities. I think it's the feature of the large corporation was much more an outcome of the meeting which took place in Orlando on February the 19th, 1982, where the industry, basically the computer industry, the semiconductor industry, and the communications industry, were asked whether there were interested parties who would march forward with the formation of a joint R&D venture. And obviously at that meeting, there were mainly large corporations representatives. Now, another feature of MCC is, of course, that the transfer of technology is not only to those who took the risk and invested in the technology, but there are specifications in our bylaws which make it feasible to transfer technology after the initial funders of the activities have had 3 years sole access to the results, that those kinds of technology developments can end up in the public domain. So there's a clear incentive to disseminate information way beyond the scope of those who fund the programs. Obviously, you need to have a mechanism where there's incentive to invest for those who take the risk up front. But I don't see any problem with smaller companies join if that's the issue.
We have time for one more. Okay, we'll use the time. Thank you. Thank you. We all know that invention is not innovation, and innovation requires the successful commercialization of the results of invention. And increasing R&D alone, though essential, is not necessarily going to improve our competitive standing in providing manufactured products and services. We recognize that in many instances we've lost our competitive ability, so that the Japanese, for example, who for many years purchased our R&D, benefited by applying their resources to the implementation of that R&D to products. We've awakened to the need to improve our competitiveness in this way as well. And our next speaker, Erich Bloch, who is IBM Vice President of Technical Personal Development, will discuss one essential element, the investment in manufacturing technology. Erich?
Thank you. If some of you thought that my title, Investment in Manufacturing Technology, had something to do with the stock market, I'm afraid you are in for a surprise, because I really don't have any experience in that area, and I also don't have any capital. So therefore I will talk about manufacturing. But that reminds me of a story. There were two friends, Joe and Bill. Joe had the experience and Bill had the capital, so they went into business together. And after a year, Bill had the experience and Joe had the capital. So the subject of manufacturing technology and investment in manufacturing technology is a very important one. The U.S. manufacturing picture needs a lot of new focus, as was mentioned just a minute ago, because it's a very important kind of an undertaking in our total economy. It's an important subject because manufacturing is undergoing a very fundamental change, even a revolution. Also, it's a basis of the competitiveness of U.S. industry vis-à-vis its trading partners worldwide. And as was mentioned a second ago, it really has fallen behind in our attention, and it needs bolstering both from a financial viewpoint as well as from a human resources viewpoints. And all segments of society, in the industry, academia, professional societies, government, have a role to play in making this happen. And I think over the last couple of years, a lot more focus has been put on this particular subject, and witness to that is the fact that an IEEE Convention on U.S. Technology Policy has that as a subject on its agenda. I'm sure 5 years ago you wouldn't have let me on this agenda at all. So I don't want to dwell too much on the first subject, namely the U.S. business environment, as we are first in innovation, but are not always first in exploiting the innovation. We're also not first in keeping manufacturing at the leading edge of technology, and I want to show that by a few parameters. The first one has to do with productivity growth, as you can see over there. We are still leading in absolute productivity measures, but not in the rate of growth, especially relative to West Germany and Japan in particular. Also, there are vast differences in total GNP between the countries. Most concerning is the direction of the growth vector that I'm showing you here in the last 10 years. At this rate, the gap in absolute terms will be closing very fast. A second parameter is capital investment, where again, we are not investing in capital as heavily as percent of GNP as some of our trading partners are doing. In fact, on this particular chart here, we are about the last in line. But capital investment and manufacturing productivity are very closely tied together. Another subject is material and equipment utilization is not what it should be. Studies in many industry sectors have revealed that these two factors are far from optimum. If you look at the material utilization, 95% of the time, material sits around in our factories and is waiting to be acted upon, waiting to be worked upon. And that doesn't speak very high on the score of productivity. Another thing that our machineries in many of our factories are sitting idle sometimes 50% of the time. And that doesn't speak to productivity. And we have to change these particular parameters significantly. Another one is the quality aspect, which one speaker this morning has already mentioned. Let me just focus you on if it's reality or perception. I think, by the way, it's reality in most of the cases, but also a perception problem. Here's kind of an interesting study that was made. Two types of groups of people were asked what they thought of U.S. products, if the quality had changed, and a group was the CEOs of major companies. 91% of them thought it had improved or stayed the same. If consumers were asked the same question, about 75% of the consumers thought that it stayed the same or had declined. Quite a gap in perception. On the second question, how does U.S. quality compare with foreign quality? 79% of the CEOs thought it was better or the same, and the consumer reacted, 75% of them thought it was the same or worse. Again, a perception kind of a problem or a reality problem. I think it's both, by the way. So all these and other issues are facing the manufacturing sector, and the question is what to do about it. So let me talk about manufacturing technology next. Like in many of technical endeavors, in the manufacturing sector also, the need for innovation is probably the main driving force to achieve productivity. This is a study from the Brookings Institute that was made many years ago and has been repeated many times since, which essentially makes this point that the single most important factor to achieving productivity improvements is really technological innovations. And that shouldn't surprise us as engineers. But many times we have not followed that particular rule, especially in manufacturing. It's not only true in the high technology sector, but it's equally true in the smokestack and the old basic industries that are suffering today from a productivity decline. Now, today, manufacturing technologies are coming into the foreground that change the whole manufacturing sector, the manufacturing enterprise, and require a different management approach than what we have been accustomed to in the past. The change is one from manufacturing process as a disconnected set of tools and a disconnected set of information handling operations to one of an integrated systems. We hear many times about the factory of the future, which I think is the biggest misnomer in history. It's not a factory of the future, it's a factory of today that we need to talk about. It's called computer integrated manufacturing, closer to the truth. Sometimes it's called flexible manufacturing, flow manufacturing, demand manufacturing, whatever the name is. Now I'm going to use computer integrated manufacturing because I'm used to the first word at least. But I think that this is what's in front of us. We are seeing the effect of this change in the direct and to indirect ratio. The indirects in our factories are increasing, reflecting the new approaches and the impact of the new technologies. Also in the percent reduction of the employment in the manufacturing sector, as compared to that of the information and service sector, you're seeing essentially what's going on underneath. The viewer model that we need to keep in mind is that of manufacturing consisting of two parallel and intertwined activities. First of all, the hardware aspect or the hardware track. It's an automated physical plant that is making the goods and the products, consisting of smart tools, robots, numerical control machine tools, test stations, with transfer stations and loaders in between. But the second track, the parallel track to it that is highly intertwined, is equally important or maybe even more important, and is the software aspect of manufacturing. Computer hierarchies that control manufacturing, integrated databases that are accessible, computer controls in tools and equipment, materials, resource planning, inventory controls, and so forth. The second track, this parallel track, is the one that, combined with the first one, is really the revolution that I talked about before. Today, most computerized factory systems exist more or less as islands of automation in design, production planning, material handling, assembly, inspection, and so on. The task ahead is to link these islands into a total system. Both hardware and software track must be addressed simultaneously to be successful, and together there's a computer integrated manufacturing. They require a new relationship between employees and management, a new relationship within management, and new materials, new tools, new equipment. Some of these systems exist today, too few, by the way. The pieces exist. The fact is that what is missing in many installations and in many operations are the interfaces, the bridges between computerized design and computerized manufacturing, between individual machines and machining centers, and between functions, other functions. For example, CAD systems, which generate the design data about the products to be produced, must feed their output into the factory process directly. This kind of systems approach can improve the designer's productivity, the logistics of the manufacturing operation, and ultimately the productivity at every level. Let me be more specific about the CAD-CAM and technology. You're seeing here essentially a plot of what it has accomplished in two areas, namely the mechanical design area and the electrical engineering area. And you see that essentially the electrical engineering area today is almost 100% automated. The design of it is almost 100% automated. Not so in the mechanical area. But even in the mechanical area, things are moving very fast. The benefits of this particular kind of an activity is shown here. It affects the design, the drafting, the engineering changes, the composites and drawings and everything else. It's really it has a wide penetration and wide effect on the productivity of the people that are involved in this particular process. In fact, the very relationship between research, development, and manufacturing is changing. It's becoming more intertwined, more overlapped. The interfaces are more difficult to define, they are more diffused and more vague. And by the way, all three functions, research, development, and manufacturing, require the same professional people, with the same background, with the same experience. Time is gone when one can make a differentiation in salary or in status between an engineer who goes into development or research or one who goes into manufacturing. Now, after saying all of that, let me talk a little bit about computer-integrated manufacturing and show some examples. I will give you a number of examples. The first one from IBM, which is called, which has to do with the semiconductor line that is fully automated. It's called a quick turnaround timeline, which I will define in a few minutes more. First of all, as I mentioned before, this is a product that it produces, a highly complex and ever-increasingly complex semiconductor bipolar chip. The process is complex and increasing, and so is obviously the product itself. What it is, the line itself is essentially a set of automated process control system, electronic routing system, automated data collection and analysis system, a feed-forward process control, a single wafer processing, automated wafer handling and storage system, has facilities for distribution of chemicals and contamination control, and it's a multiple part number per wafer kind of a system. So it essentially has all the ingredients of what I defined before as a computer-integrated manufacturing system. Here are a few views, a couple of views of the line itself, and I really don't want to dwell that much on that, but let me point out one other thing, that underlying it is essentially, or overlaying it, if you want to put it that way, is this parallel track that I talked about before, namely a complete systems architecture, a multi-level system architecture which ties together everything from the tool itself to the ordering system and to the shipment at the output dock. The justification for this system is not cost, but it's turnaround time. It's the quickness of getting a new part manufactured. The capability of designing almost an infinite part number set by demand part numbers. It's quality, which is very important, and essentially the effect of all of it is a shortened development cycle. Notice I haven't said anything about cost. Also, all of these ingredients add up to cost. It's the primary motivations were some of these. Show you a couple of other systems. One from Japan, the Fanuc system, which essentially manufactures parts for robots and machine tools. And you can see essentially from the justification on this particular slide here that the capital investment is a lot less, factor of 10 over a conventional facility. The labor force has been reduced by a factor of 10 also, and the productivity improvements have gone up by a factor of 5. There are also systems in the world in existence in GE and John Deere. Let me just talk about John Deere for 1 minute. And this obviously is the tractor works. And here again, I won't go through the application. You can imagine what that is yourself. But the justification for the system is, first of all, to build a tractor in twice as fast as before, to reduce the inventory that this company has to carry at great cost, and the ability to compete with short liners, with short runs, no longer this economy of scale kind of concept, and to attract new business so that new business opportunities can be handled on the same line, or economy of scope, as it's called many a times. So these are some of these examples that I wanted to describe to you. By the way, let me say one thing. They all have about a common kind of underlying principles and concepts. They're not easy to implement. They must bring together a wide variety of technologies, and they force us to rethink the whole process and the management system a company employs. The small number of these systems in existence today is not caused by the lack of technology, but a lack of management resolve and management conviction. These systems also have as a paramount ingredient new management concepts, new policies on inventory, to have no inventory. That's a good policy. New ground rules on receiving inspection, namely to have no receiving inspection. New requirements on component reliability, no longer a couple percent bad parts in a shipment, but parts per million of bad components. Point of use manufacturing and demand manufacturing versus offshore component vendors or off-site kind of vendors. These are vast changes that we should not underestimate. There are vast changes in technology, there are vast changes in attitudes, in policy, in corporate culture, even in government attitudes, and some of it was mentioned before by the previous speakers. Let me talk now about recapturing U.S. manufacturing leadership. I try to show the status of U.S. manufacturing, changes that it is undergoing, technology driving forces behind it. What are the requirements? First is to address the question how we recapture that leadership. Well, I want to say very clearly that I'm optimistic on that point, that it is possible. And the new technologies and the new approaches certainly are key to making that happen. There are three important areas. The first one is the need for systems approach in factory automation. The second one is how to use a workforce more effectively and what kind of workforce is required. And the third one is the area of critical skills. Let me not dwell on the systems approach to manufacturing automation. I talked about it and I showed some living examples. And also the reasons why these are being pursued. So the second and the third issue is what I want to identify that is needed to recapture this manufacturing leaderships. There are new relationships between management and its employees and need for critical skills. The new manufacturing environment requires a well-trained workforce, well-motivated, that accepts the new developments and the new technologies. It must be part of the decision process, must be given a chance to be trained, and its job scope broadened. This part of the new manufacturing job is more important than everything else that I discussed before. We also need an adequate supply of manufacturing engineers with production skills who know automation and how to manage quality, and are people that are educated in the systems aspects of manufacturing. It requires a broad range of skills, quite apart from, but in conjunction with product innovation. The old manufacturing connotation should be really replaced by the manufacturing process engineer connotation or the manufacturing systems engineer connotation, because it reflects much better the new environment.